We're told the maximum normal stress we can have anywhere in that cross section is 180 megapascals. We want to find the maximum force P that we can apply before we're going to have failure in our material. They're telling us to cut across that plane AA, and we're going to see pretty quickly here we're going to have a problem. This is actually a 2D problem, not a 3D problem, so in that case it's a little bit easier. But if I'm cutting across AA there, and at that cut surface, because I'm only in 2 dimensions, I'm going to have 3 internal forces. I'm going to have, I'll actually call it N in this problem for that internal normal force, just so we don't confuse it with this P. Potentially some shear force, but we know it's going to go to 0. And my bending moment M. Distance between my where my internal loads are acting and force P. What's our assumption of where the internal loads act from? We always assume that the forces emanate from the centroid of our cross section. So we're only told it's 200 millimeters to that right edge of it. We need to find where is the centroid first before we know how far are these loads from point P. Okay, so stick with that original coordinate system I established. If I place x right and now z up, I'm really finding how far in the x direction is this centroid. So if I go through the first part of the table, I find it's to the left of the axis by 26 millimeters, which means the distance between P and the Q, where the centroid is located, will be 200 millimeters plus 26 millimeters. So this distance will be 0.226 meters to stick everything in base units here. Right, so filling out the rest of the table, we get that the moment of inertia around the z-axis, or the neutral axis parallel to z, 477,000 millimeters to the 4th power. But again, we were going to want to go everything to base units, so we'll get 477 times 10 to the negative 9 meters to the 4th power. And so I need to know N, I need to know M. So first, sum of forces X right away will tell me that that internal shear force will be 0, which means I won't have an internal shear stress here, just normal stresses. In the y direction, I'll have negative P plus N. My moment around Q, I'll have positive M minus 26P. So that internal moment is 0.226 times P. That internal normal force is just equal to P. So if I want to know what is the total stress so where would the stress be, normal stress be maximum in the shape? Because we have to make sure that we don't go above 180 megapascals. Now it doesn't tell me to consider both tension and compression here. But we can't go above 180 or negative 180 megapascals, but where would that happen? Right, the edges, so the far left or the far right it could happen. So these 2 places are where we would have to consider it, because P over A is uniform across the surface. The My over I will be maximum at in this case, the top, or with respect to this neutral axis, the bottom and the top. So these are the points we need to check to make sure that it's not above a compressive 180 or a tensile 180 when we find out what the value of P is that's going to cause that. So yeah, in this picture, M is going to be around the neutral axis in this direction. So we have to be concerned here that this does not exceed the tensile 180, and this does not violate the compressive 180 when we're applying this force P. But P is going to be in the direction that we, pointing in this direction, so we know N is going to be positive. So we have to be careful with our signs when we formulate this. So let's first look at what I will call the top. Now this would potentially fail in tension or compression. Does it look from the picture? Right, it'll have the tensile stress from P pulling out, and on top of that, a tensile stress from the bending stress, M. So we want to make sure that this does not go above positive 180 times 10. Stress due to the normal, N equals P, so P over A. And then we'll have another tensile stress due to My over I. Our M value, 0.226 times P. The I value we found previously. This is another case where we know it's tensile, so we can control the signs on M and Y ourselves. We need to go, you have to look at the top here. So our distance from the neutral axis to the top will be the 26 millimeters. So for it to fail in tension at what I'm calling the top of the beam here, we would have to apply a force of 13.4 kilonewtons. And what we would find, I won't go through it, but if we put in what would it take for this to fail in compression, it's going to take a negative value for P. So if we're assuming that we are pointing P in the direction that it says in the picture, then we only would have to be concerned with this failing in tension when the value of P is 13.4 kilonewtons. But again, we also have to consider that the other side could fail in compression because M is going to cause a tension to the right of the neutral axis, but a compression to the left of the neutral axis. So our fear at the bottom is that it fails in compression at negative 180 megapascals. The stress from the normal stress from the axial load is going to be the same. That will still be tensile. But the bending stress, we know, will be compressive. So this will be a negative out in front. The bending stress is compressive. The axial stress is positive. So negative 0.226 P times this distance, which is going to be 70 millimeters minus 26. And the value of I remains the same. Right, so again, the differences here, this is compressive, so this term is negative. But also the distance between the point and the neutral axis is different. It's 44 millimeters rather than 26 millimeters. So here, the amount of force required for it to fail in compression on that left-hand side, we're going to get 9.01 kilonewtons. Again, same thing as at the top. If I want to see what the value of P was that would cause this to fail in tension, I would actually get a negative value for P, presuming that P has to be facing the direction that it was drawn in. It would fail in compression when we have a 9 kilonewton load. All right, so it fails at the top in tension at 13.4. It fails at the bottom of the beam in compression when we apply a 9 kilonewton load. So what is the maximum value we can apply before we have failure? Right, it's the lesser of the two.